So let's review some examples of the kinds of problems you should be able to do from chapters 6 and 7. As we go through these, pay attention to what the question actually is. What am I asking you to come up with or give me in each problem? Number 1, the heights of 18-year-old men in the United States are approximately normally distributed, with mean 68 inches and standard deviation 3 inches. What is the probability that the height of a randomly selected 18-year-old man will be between 66.5 and 72.5 inches? Notice the question is, what is the probability? So that's what we're trying to find here. This is a question where we're finding a probability of that random variable, the height of a randomly selected 18-year-old man, being between 66.5 and 72.5 inches. We're also given the information that the mean is 68 inches and the standard deviation is 3 inches. So we need to find the probability of x being between 66.5 and 72.5. If you're doing this by the table method, you would first convert both of those numbers to z-scores. 66.5 converts to negative 0.5, and 72.5 converts to 1.5. So now we need the probability of z being between negative 0.5 and positive 1.5. So you would look up those z-scores on table E and subtract the numbers it gives you. 0.9332 minus 0.3085 equals 0.6247. If you're doing this using the graphing calculator function, you would ask it for normal CDF. You would give it lower and upper limits of 66.5 to 72.5, and you would tell it that the mean is 68 and the standard deviation is 3. Number 2. At an office supply company, the lengths of phone calls by customers placing an order are normally distributed with an average length of 5.4 minutes and a standard deviation of 0.9 minutes. What is the probability that a sample of 9 phone calls will have a mean length of less than 5.0 minutes? This one is also asking us for a probability. The difference this time is that it's asking us for a probability not for an individual value to fall within a certain range, but for a sample, a group of values to have a sample mean within a certain range. In this case, that sample of 9 phone calls will have a mean length of less than 5 minutes, 5.0 minutes. So here we need to find the probability of x bar, not just x, but x bar, being less than 5.0. To convert that to a z-score, since that's x bar, we use the formula z equals x bar minus mu over sigma divided by the square root of n. So that would be 5.0 minus 5.4 divided by 0.9 divided by the square root of 9. When you put this into your calculator, remember you need parentheses around both the numerator and the denominator. So if you put it in correctly, it should give you negative 1.33. Now that we've converted to a z-score, to get the probability of z being less than negative 1.33, we would look that up on table E. And since this is asking for the probability of z being less than that number, the number we find on table E is the answer to that question. We don't need to do anything else with it. So the answer is what we found on table E, 0.0918. If you were using the graphing calculator function, you would find the normal CDF from some really low negative number up to 5.0 with a mean of 5.4 And for the standard deviation, you would put in 0.9 divided by the square root of 9. That whole thing is the sigma for x bar. Number 3, for what negative z value is the area under the standard normal curve to the right of that z equal to 0.08 or 0.8708? So here what it's asking us for is a negative z value. So when you write down the answer to this question, that answer that you write down should be negative and it should be a z value. Now it's asking for a negative z value under that standard normal curve to the right of, so that the area to the right of that z is 0.8708. If the area to the right of z is 0.8708, the area to the left of z, which is what we have to know to find it on the table or to put it into the calculator, must be 1 minus that. 1 minus 0.8708 is 0.1292. So that's what we look for on the table, and we look for it in the middle of the table, where those areas, those 4-digit numbers are. And when you find it, the z that goes with it, when you look over to the left and up at the top to find the digits that make up the z, it's negative 1.13. So that is the answer. To do this on a graphing calculator, you'd still have to subtract from 1, and then you'd ask the calculator for inv norm of 0.1292. Number 4. Oh, and by the way, the questions we've done so far, the first question was the kind of thing we talked about in section 6.2. Second question was the kind of thing we talked about in section 6.3. And what we just did was one of the things we talked about in section 6.1. Now, question 4. A company is planning a management training program for the top 18% of its employees as measured by their scores on the skills test. If the scores on the test are normally distributed, with an average score of 400 and a standard deviation of 50, what is the cutoff score so that 18% of all the scores are above this value? Can you see what it's asking for so that you know what kind of question this is? It's asking what is the cutoff score so that 18% of all scores are above this value. We want the score on the test that separates the top 18% from all the rest. Now, before we go to the table or before we go to the calculator, we need to know the area under the standard normal curve to the left of that cutoff point. That would be the percentage that is below that value. Now, I might ask you a question where I give you the percentage below the value, and in that case, you don't have to do this. But in this one, we know that 18% is above the value, so the other 82% would be the percentage that's below the value. So that would represent the area under the standard normal curve to the left of the cutoff score. So that's what we need to look for on the table, or to give to inv norm if you're using the calculator. So if you're using the table, look in the middle of the table where those 4-digit areas are, and look for the closest thing you can find to 0.8200, which turns out to be 0.8212. And that goes with a z-score of 0.92. And then once we have a number for z, the way we get our final answer, our x, is we use the formula x equals z times sigma plus mu. So that would be 0.92 times the sigma was 50 plus the mu was 400, and so that gives us an answer of 446. And I didn't say it on here, but If you have a graphing calculator, you can just ask it for inv norm of 0.82 and tell it the mean is 400 and the standard deviation is 50, and it'll give you the answer. Number 5. A researcher wants to determine, to within $1,000, the average salary of third grade teachers. She wants to be 95% sure her estimate is correct. If the standard deviation is $2,900, how large a sample does she need? So this is a question of how large a sample does she need? How big does the sample have to be? It's a question about sample size. Now, we've actually seen two different formulas for sample size. One was for sample size for means, and the other was for sample size for a proportion. Can you see which one of those we're doing here? She wants to determine the average, that is the mean, of the third grade teacher's salaries. So to do that, we're talking about sample size for means. That would be this formula right here. You're not going to get the right answer if you're not using the right formula. So before you start plugging in numbers or doing any of that, make sure you know what kind of question this is, what it's actually asking for, and what formula we have to use to answer that question. So with that formula, we have to plug in numbers for z sub alpha over 2 and sigma and e. For a 95% confidence level, the number we use for z sub alpha over 2 is 1.96. Sigma is our standard deviation. We're told that's $2,900. And E, well, it says she wants to determine to within $1,000. So that's how close we need to be, how big a margin of error we have. So that's the number we put in for E. Then when we plug all that in, do the calculations, the calculator spits out 32.3 something. But you can't go out and get a sample of 32.3 teachers. It has to be a whole number of teachers. And if we round down and just take 32 teachers, that might not be enough. That might be a little bit too small of a sample. So for sample size, we always round up to the next highest whole number. And in this case, that would be 33. So she needs a sample of 33 teachers or more. If she has more, that's okay, but she needs at least 33 in the sample to get the kind of accuracy she's looking for. I'm going to end this video right here and then come back in part 2 and go through, we've just got a few more of these review questions to go over. So see you in part 2 of this video for the rest of the review problems.